one or more hidden layers where it could have no hidden layer as well, but usually it has. What it does is that it weights those inputs with certain weight functions and biases, and then acts with some activation functions on them, and then repeats them, adjusting the weights and so on. And finally, it gives you a certain output. So the punchline is that you send an input vector, you get an output vector. In our case, however, we're going to send an input vector, and our output is one dimensional, so we will get an output scalar. And whatever weights you draw in these hidden layers, they are probabilistic, and as you train it, the weights get updated. However, in what we are going to do today, there is no training involved. Everything we talk about is at a frozen step. You can think of as a um, like if you divide your training as discrete steps, then we have frozen up the picture at some particular step, and we are talking about that step. And the simplest one is the one at initialization at t equal to 0, or the zeroth step. Okay. So, what is a neural network field theory then? So it is a statistical field theory. I'm not going to call it a general quantum field theory per se. I'm going to just be conservative and call it a statistical field theory where the fields are constructed from post-activated neurons. So you can write some phi of x, what your field is, as sum over weights and some post-activated neurons. HIs are some post-activated functions. Uh, Now, because the weights that you draw in A and also in H that are there are random, it is probabilistic. Uh, if you write phi x equal to something and you draw them from the distribution, every time you're going to get a different number for phi of x. So the probabilistic nature of the fields are coming from the probabilistic nature of the parameter draws. So whenever we have to talk about something, we are going to talk in expectation values. We are going to compute correlation functions by taking expectation values in the parameter space. The parameter space are the weights. The parameters are the weights that come in here, and the space of all parameters is the parameter space. So you can compute, for example, let's say 2-point function to be some expectation value over the A's and other parameters that appear in H, and just put these two fields there. So in this formalism, we are not drawing fields from an action. We don't have an action to begin with. We begin with a field, and the goal is that whatever interesting you have in an action, maybe we can design those interesting features at the level of field itself and study them. That's the hope. So let to summarize what I just said in very one more time. So the network goes from space-time to fields. So input vectors is the space-time vector, and the fields are output. So it's a phi is a map. The parameters are drawn at initialization at the t equal to 0 step from certain distribution. Now, of course, this there are many constraints on what this should be to get the desired type of correlators, and the statistics that you compute using expectation values, they give you the correlators. So that's the philosophy of this approach. Everything is going to be first principle from here. Okay. So just to remind or to familiarize people who may not be familiar with CFT, uh, the conformal group is a set of transformations that preserve angles, and it includes 4 transformations mostly: um, the translation, the dilatation, the rotation, and the special conformal transformation. So in ordinary quantum field theory, in ordinary Euclidean quantum field theory, you usually have this translation and the rotation. So these are the extra two things, that's dilatation and the special conformal transformation, that is there in a CFT. We are going to use one special relation, um, which is a group isomorphism between the conformal group in d dimensions to the Lorentz group in d plus 2 dimensions. So they are both SO d plus 1 comma 1, and you can explicitly map the generators from one side to the other. So if you're in the light cone coordinates in the d plus 2 dimensional Minkowski space, uh, then your generators, the rotations maps to rotations, the scaling takes this um, off diagonal value, and the translation and the special conformal transformations are whatever the extra coordinates that we have, plus and minus, with respect to each space time direction in d dimensional theory I. Okay, so in this embedding
Sorry,
formalism,
how do you define this L plus L minus mathematically? I mean,
yeah, I'm coming to that.
okay.
uh, uh, oh, you mean that how do you define this L plus L, this thing? Like,
Yes, yes.
it's just the Lorentz generator along that direction. You just make a coordinate transformation in the like in your Minkowski space, and
Okay.
then it's just a Lorentz generator.
I see.
So
Thanks.
so uh, in this embedding formalism, you make use of something called the projective null cone. So you had two extra coordinates there. So you're going to impose s- some constraints to uh, get a d-dimensional subspace where in which you can where you can talk about the theory to be actually related to the conformal field theory in d dimensions. So if you start with a d-dimensional Euclidean space. So this is for the this small index are for the conformal field theories, like the CFTs, and the large like the capital index is for the Lorentz space, the higher dimensional space. So you can construct a vector that looks like this, um, and you define a metric that looks like this. In this metric, because it's a null cone, that's why we have, if you have a vector, then x dot x will be equal to 0. And on that null cone, we are going to uh, choose this number one that we choose. This doesn't have to be number one. So this can be some other numbers, and accordingly, the other vectors are rescaled. So for convenience, we have chosen it to be one. So the point of this thing is that on this PNC, you can define a field with the x coordinates, the capital X coordinates, which can be identified equal to the uh, conformal field that you had in your original d-dimensional conformal field theory. So, and they must satisfy this homogeneity, that the fields in the D plus two dimensional space, that if you scale your coordinate by lambda, then your fields scale by lambda goes to some negative minus negative delta, where this delta would be the scaling dimension. So so we are kind of taking one slice of it, like in this null cone we are taking like one slice of it. So if you come away from here, you're going to get a different lambda, and accordingly you will have to shift your field. So uh, for our purposes, we're going to just sit on that one slice and do everything. And coming to the other slice, it's going to give you the same theory, just a rescale version. Okay. So how do you compute correlators in this in this space? You compute correlators. They look like something like this. The so in the usual conformal field theory, the 2 point functions and the 3 point functions have their forms fixed, and they look something like this. That between x and y, it scales as x minus y to the power 2 delta 1 over 2 delta. So on the embedding formalism, in the embedding coordinates, this goes as x dot y. So x dot y is actually minus one half x minus y whole square. So for in this talk, I'm going to suppress that minus half everywhere, uh, and just consider them to be like equivalent. Similarly, if you have a 3-point function, then its form is also kinematically constrained up to a coefficient which is called the OP coefficient. Uh, and you get some form like this where the alpha ijk's are defined such. So in usual CFT story, this C55, this is like always said to be 1. But in our talk, like in what I'm going to discuss from now on, I'm going to keep this coefficient not 1. And because I have not set this to be not, I have not normalized this. I'm going to use it later when wherever it should appear. Okay. So another important thing, like another useful thing that you can do in CFT. Um, so the 3-point functions are all constrained. Uh, what about the 4-point functions? It turns out that the 4-point functions have freedom uh, in what they could be, and they enclose or they encode the interacting nature of the theory. So, and they can be expressed in this form as in equation 9, that you can write them as G U V Y. This when you have four scalars, same scalars, then you can write it like this. And this GUV is a function of cross ratios. So cross ratios are something that are themselves conformally invariant. And if you make any kind of transformations, uh, this U and V's are like they will be same. So what we can do next is that it's a powerful technique in CFT that people use is the conformal block decomposition, where uh, you can write this GUV as a sum over some conformal blocks which belong to I denote this G delta O L to be the conformal block associated with the conformal family of the primaries appearing with some coefficient. Uh, in usual story, this coefficient is um, of course, up to the normalization of just G is the square of the OP coefficient. But because in our case we have not we don't have normalized 2-point functions, so I'm just gonna take this number to be a positive number. So solving a CFT means that so here all those O's appear that appear in the uh, operator product expansion of the phi and phi operators, which I have not defined though. So solving a CFT means it kind of means that you know all these CFT data. The CFT data are nothing but the list of all scaling dimensions, their spin, and the OP coefficients. And if you know all the CFT, if you know the CFT data, then you can reconstruct the correlation functions and the S matrix. So in principle, knowing the CFT data means that you know the theory. Uh, so our goal would be to solve for this CFT data in this formalism. So I'm going to take a particular strategy. This is not the only strategy. This is just one strategy. You could use some other strategy. Um, so in this framework, I'm going to take this strategy that I will first build a Euclidean invariant homogeneous architecture. Then I will recrotate it to get a Lorentz invariant homogeneous architecture. And then I will restrict my correlators to the projective null cone. The and the requirements that I'm going to require from the network and also from the fields is that whatever the function output function for the field I choose, uh, that must be homogeneous. Now you can choose it in any way you like. You can nest it and so on. At the end of the day, it just should be homogeneous. and the parameter distribution that you are taking for the like probability distribution for the parameters that you're taking, that needs to be rotationally invariant. This is required to ensure the correlators are also rotationally invariant. And the most simple thing you can think of that satisfies these two conditions is equation 12. And we will take the most simplest version where delta is equal to -1. That is, phi would be theta is equal to phi of x would be theta dot x. So let's consider an Euclidean field theory in d plus 2 dimensions.
Uh, Joydeep, can I ask a question?
Yes.
So, is there a reason you have to go to this embedding space formalism? Can't you? Is it hard to directly encode conformal invariance in d
Um,
dimensions?
yeah, I mean, it helps. The embedding formalism helps. It makes it easier.
I see.
I, I'm not
So
aware of any. Yeah, please.
so somehow you're able to encode rotational invariance in the parameter distribution.
Yeah, that's right.
So, is it hard to do encode the full conformal invariance in the parameter distribution?
That's right. That's usually because translation invariants and scale invariants, they don't go well together, and I'm not aware of any distribution, um, at least in standard literature, that has that symmetry. So so it's it makes it easier for us to go to the embedding space and start with the Euclidean distribution.
Okay, thank you.
Cool. So we have our field. Now we are going to compute the like say 2-point function. So in the Euclidean theory, if I compute the 2-point function, what I'm going to get is that expectation value over this one theta coming from one field, another coming from the other, and because of this delta ij. So we are assuming IID parameters. Uh, because we are assuming IID parameters, when the two thetas are not same, they are just zero. So only the theta square will contribute. So you get something like equation 14. Then you Wick rotate your Minkowski metric uh, and and restrict to the Poincare null section. The restriction to the Poincare null section ensures that if you have terms like x dot x or y dot y, which we don't have here, then they go to zero. So there is another example in our paper where those terms appear and they go to zero, and so this is needed. So
Sir, Joydeep, one
yes,
more question. Can you explain again how do you restrict to this projected null cone? So do you just take input values that are on the null cone?
for the theta,
No, no. So if you go back to the previous slide,
yes,
no, the previous slide where you had the neural network.
sorry, this one,
Next one.
uh,
Yeah, after
this one,
yeah,
yeah,
this one. So here, so this is homogeneity,
yes.
the first part. So how do you restrict to the to that slice?
So I only choose X that belongs to that slice.
Yeah, so the input is just taken to be on that slice. That's it, right?
Yeah, it's taken.
Yeah. So it's not like a random d plus two numbers. Those numbers have to satisfy those
Uh,
conditions of given slice.
Random d plus two numbers, like if you take them, then um,
Yeah,
like
they won't belong to the slice.
they won't belong to that slice. That's
Yeah.
right. They won't belong to that slice.
Yeah. Okay. Okay.
Yeah. So so you compute your 2-point function just like this. Now I skipped the 1-point function thing. So if you think of it as in terms of the, if you just want to compute the 1-point function, then um, if you take just the x, anything that is odd in x, then this expectation value of some odd number will make it 0. So they are anyway 0 from here. And if you take something even, then x dot x, because it itself goes to 0, then that will go to 0. So the only operators that that have a non-zero vanishing uh, one point function are the ones that do not have any kind of x and y. So essentially they are dimension 0 operators, which in a local unitary theory would be the identity operator. Okay. And if you compute some phi of x with some other phi of k, because I told that before that these functions are constrained. If this is okay, I didn't write that. So if you take two different operators of two different scaling dimensions, they are 0. So how do you verify that? We verify that here, that you take some other phi to the power k, um, and you compute it. Then because if it's odd, then they get 0 by this, again, this expectation value thing. And if this together they're even, then y would be like y, there'll be some point remaining that goes to y dot y, and they will just be 0 by default on the PNC. So similarly, one can compute the 3-point functions as well, and also the 4-point functions, and then re-express them as in the form of the 4-point function that I showed before. Now, um, now that we have this got this equation 18 the from 4-point function, can we do a conformal block decomposition and understand what are this spectrum of operators that would appear if we take a phi op? And so it is just convenient to change the variables, although I'm not doing anything explicitly here. So in this you fix the dimension. I could have chosen d equal to 2 as well, but I fix it to be d equal to 4. And when I fix d equal to 4, so then d plus 2 is 6. uh, uh, this the conformal, like this g, the small g that I had, that can be written as blocks of these two operators, one that is a scaling dimension -2, and the other that has a scaling dimension 0. And we have these numbers that are appearing from the conformal block decomposition, uh, which are like which depends on the moments. Now the question is that by doing the CBD, it tells you the spectrum. It tells you what operators are like operators with what scaling dimension and spin are there in the theory, but it doesn't tell you the ansatz for the operator. It doesn't tell you how the field looks like, what is the form of the field, because in our work we started with the explicit form of the field, right? So we would like to know that. And how do we know that? I'm going to derive this operator spectrum. So um, let me propose that the ansatz for these two operators, the one with zero, like the one with scaling dimension 0 is theta dot theta, and the one with scaling dimension -2 is theta dot x whole square. I'll tell you why I chose this. So this gives us, if I want to compute then what this p00 should be, um, then I can express them as the coefficient that appears in the 3-point function squared by the normalization that I didn't consider before for the 0 0 operator, and similarly for the um, delta equal to -2 operator as well. And these quantities are something that you can compute by weak contraction. And what we have here is that they match the values. If you take this and that's for the field, then they will match the values that you have obtained in the CVD in the previous slide. So why does this ansatz work, and why did I choose them? I chose them preserving the homogeneity of theta. So what I mean is that uh, so you had one phi here. So this phi looked like theta dot x. So there was a theta here. And this had a phi. It had a theta there. So there are two thetas. So any operator that appears on the right hand side, they should also have two thetas. Um, doesn't Irrespective of their scaling dimensions, and that's what we did there, and it matches. So but this is a very simple correlator, like you take all the fields to be same. So can we do it for other correlators like phi square, all phi square correlators? And yes, we can do it for all phi square correlators and also all phi 4 correlators. Like it works. But now what about mixed correlators when you have something like this? uh, so you will have two different channels, uh, and those two channels will give you two different conformal block decomposition. So if you take this one and you take the S channel, then you get something uh, that doesn't contain any dimension 0 operator. It has a -1 and -3. And if you take the if you just alter the operator points from the x2 to x3, like bring phi here and phi squared there, then what you have here uh, is uh, is an expansion in a like a different channel. So you get again 0 0 operators and 0 -2 operators. And we by following
Sorry,
our rules.
Jaydeep,
Yes.
Jaydeep, one question. So, why didn't you consider, if you go back to the last slide,
Yes.
why didn't you consider something like theta dot x to the power -2?
Yeah, we can consider. Oh, sorry. Good question. Uh, we didn't consider because this already gives us what the scaling dimension should be, and it's a finite spectrum.
No, I mean, right now what you have is a negative scaling dimension, so it's non-unitary.
Yes,
So if you had just taken theta dot x to the power -2, you would have like the scaling dimension would be +2.
that's right.
So I'm just asking, why did you opt to do a non-unitary thing instead of a unitary thing?
Oh
Is it harder to implement that kind of
no,
architecture?
in our paper we have done that. We have taken positive powers as well, like positive scaling dimensions as well. But the technicalities of doing these computations involve are more involved, and I thought that I would just go with the easiest example. But
And
the principle is same.
yeah, and I just wanted to know, so do you actually get these numbers out from a neural network?
Uh,
In a sense,
no,
I mean,
we just
because there's no
compute them.
training right now. It's just
There's
the
no
neural
training.
network at initialization.
Yes,
You so what you're basically should be doing is you pick some distribution which has that symmetry, uh, the rotational invariance, and you
yes,
pick inputs that lie on the slice in the projective
yes.
null code, and then you just initialize, let's say 10,000 times whatever, and
Yeah,
then you just average over all the initializations, and yeah, you compute the correlation function. That's what you're doing, like.
yeah, that's what I'm doing. You can do that on a computer writing a code, and you can also do that analytically by taking the width of the neural network to infinity. Like there are infinite number of nodes. So actually I have been using that as assumption for a while now, that the fact that I computed an expectation value here, it assumes like if I had a finite one, then I would have just written that them down and averaged it. But the fact that I'm doing an integral here and taking an expectation value is kind of a consequence of the fact that I'm taking my neural networks at infinite width. But if you
Okay.
don't take any finite weight, if you take, let's say, 10,000 neurons, and a million neurons are even better, then you will. I think from 10,000 itself, it starts matching the analytic answers.
I see. So is this some sort of if you take this infinite width, is that like free theory, or do you still get like non-trivial 4-point functions in this infinite width limit?
I mean, when you take infinite weight, then you can um, like then you are like the expectation value that you are writing, you are actually able to compute that uh, as an integral.
I see.
Uh,
You mean for
Otherwise,
analytic? Is it for analytic purposes? Of numerically, of course, I could do whatever.
yeah, numerically you can do whatever you're free to do. You like you, something like 10,000 is a large enough number where you can do this, and you will get your answers exactly same what you'd get from an infinite weight network. So it's okay. So I think that maybe I should speak a little bit about it. So uh, maybe I should have included that. So
So just my question is: are you doing free CFT calculators,
no,
or
we are
is
not
it
doing free CFT. This is not a free CFT. This is interacting CFT.
okay? Even in the infinite width limit, it's still an interacting CFT.
Yes, even in the infinite width limit, it's an interacting CFT.
Okay. Okay.
Yeah.
Okay.
So
Thank you.
there's something called Google's neural tangent kernel. What they do is that for very simple neural networks, they take an infinite width limit and they try to predict the outcome of training by analytically taking this infinite end limit and doing these integrals. And what we are doing is that we are freezing, like, so we I talked about initialization. You could have taken some other time step of the training process as well, as long as they respect this symmetry. So if you are in some other training step of the training process where your probability distribution function has changed, it has altered, but it still respects the symmetry, then you still get a CFT out of it. But what would change is the values of these moments of the distribution. The CFT data has changed in that case.
Yeah.
Is
Yeah.
it
I
clear?
understand. Yeah.
Okay,
I
cool.
understand.
So we can also compute this by weak contraction, and they will match the values, like they match the values obtained in the conformal log decomposition. Oh, I was in this case mixed correlators. So in this case also we can compute the OP spectra of both these channels, and the P P delta Ls can be actually computed. Okay. So now I can take a different limit. So initially I was at the infinite width limit of a single network. Now I can take an ensemble of networks. And if you think of a single network as an ensemble, you can think of this as an ensemble of ensembles. Okay. uh, and then you can um, uh, this phi I was, let's consider this to be the field that we were talking about so far, or some other field with some other scaling dimension, positive, negative, whatever you like to, uh, and you just sum them over a large number of them, let's say capital N of them, and you define a new field using your old fields, using like a linear combination of your old fields. Okay. If you do that, uh, then again you can compute certain 4-point function, and in this case the 4-point function would look like this, where you would have a fourth moment that would be related to the, so the the fourth moment would relate to the um, 4-point function that the GUV that you'd get for one particular phi, like what you'd expect from each of these phis. And there would be other terms that is coming because there are n many of them, which would look like this. So now if you take the n tending into infinity limit, this portion where it was an interacting theory, this portion goes to 0. It gets suppressed, and what you are left with, some 1 plus u to the power uh, delta, and plus u plus v to the power delta. I'm sure this is very familiar. This form is very familiar to you all. uh, so what I will get is some generalized free theory in this limit. So now I will prohibit myself or restrict myself to the positive scaling dimension case where delta is equal to +1. I'm not going in the details of computing of how do I compute correlators from this kind of theories? These integrals are in general difficult, and you have to impose like when you, because these are multidimensional integrals in parameter space, and the trick that we used were Feynman integrals that amplitude people use. Uh, but in principle, if you're able to solve those integrals, if you're able to do those integrals analytically or numerically, then then you can actually handle this theory. Okay, so if I specialize myself to this delta equal to 1 thing, then my conformal block decomposition from here, this it would be just 1 plus u plus u by v, and that 1 plus u plus u by v, as you all know, is the like in 4 dimension, it's just the like it's a free theory, right? Free scalar theory. And if you do a CBD of that, then you get an infinite number of like twist 2 primaries. Uh, um, and because now when you get this, you get some operator that has a spin 2 and scaling dimension 4. You will interpret that as the energy momentum tensor, and what you can do is that you know the functional form constructed out of this phi, this single field, and then you can actually write it down, and then you can compute the 2-point function for the energy momentum tensor in the n tending to infinity limit, and that would give you the central charge. And this can be done. Okay, it's a like it's just a long calculation about weak contraction, but this can be done. So
Sorry, Joydeep, can you go to next slide? The previous slide. The equation 26 is looking like inverse of a neural network. How do you implement inverse of a neural network?
this one,
Yeah.
no, it's not like an inverse of a network. My network is such that this whole thing is the function.
Oh, I see.
Like it's not f inverse, but rather it's some f prime that looks like this.
Okay. Thanks.
Okay. So what are the general lessons or from this example? What do we learn here? Uh, so the first thing that we learn here is the choice of the network architecture fixes the CFT data. So so what I mean by this is that uh, sorry, what my p of theta is, and how I uh, how I define my architecture here. Like I could have taken something very complicated and nested that still has the scaling. That construction will, in principle, uh, um, fix the CFT data that I have. The operator spectrum, although infinite, uh, are highly constrained, and the OP coefficients can be extracted. And one can in principle solve this kind of theories analytically. Now I wrote this f in bracket because the example I showed you, it doesn't have a local stress energy tensor, so you might argue that you don't want to consider this to be a CFT and so on. So according to one's taste, I would like to call it a CFT. If you don't like to, then just think of it as conformal theories. uh, but then why are we doing this? What's the like what do we do what plan to do in the future? So one powerful aspect of this approach is that you can exactly compute correlators, 4-point correlators. So that means that you know the exact GU, like the GUV from the 4-point function. And in the conformal bootstrap program, uh, what people do is try to constrain the theories, but they don't really know the exact correlator. Uh, so this is just one thing that can be taken advantage of. So the future would be that take lessons from these toy examples to do interesting theories. And one thing that we are working on right now is you start from a toy example with the toy theory, and then you can use neural networks themselves to flow to a more interesting theory. And that would like the hope is that this method might allow us to do things that are that were more difficult to do by other methods. Uh, that's the hope. And if you're a mathematician, if you're more interested in math, then this was pointed out by Professor Sylvain Rivault, that these are related to harmonic analysis. And the fact that I get OP spectrum that I'm solving, uh, uh, this is very similar to what they, and this approach is very similar to what they do in hyperbolic orbifolds. So you can take a look at this if you'd like. So I'll give you now one backup slide, one example where it's not CFT. It's just a cosnet. So cosine is my activation function now. So what I can do is that I can define my phi to be sum over some up to k parameters AI, and this a, some post-activated neurons LIs, and this LIs, let's say they have this functional form, and you can draw your AIGs and BIs from some normal distribution, not the same, different but normal distributions. Then what you would get is the statistics would then be give you something that looks like this. So if you look at this type of functions, uh, these theories are Euclidean invariant theories. They have translation invariance, rotation invariance, and uh, this can be used to construct just free quantum field theories. So this is another example. If you're interested in cosnets, which is something that people use in actual neural networks for their actual solving of industry problems, more close to the industry, then please see this reference. Thank you very much.
Are there any more questions, comments from anyone?
Yeah, Jaydeep,
Okay.
I have a question. So let's say I don't want to do things numerically, analytically. I just want to do it on a neural network.
Okay.
Then what am I really doing on a neural network? What does this procedure look like? Uh,
I mean,
so you already, let me just tell you what I understood. You already start with some fields whose scaling dimensions are fixed by
yes.
the architect.
Yeah,
Uh,
I define one field, and then I try to understand what other fields from its 4-point functions and interpretation as OP, what other fields appear in the spectrum. Like if I have a theory, then what other field should be there? But I have to start
yeah,
with one field.
yeah. Let's say you start with some field, and basically you're making a neural network ansatz for that field, and that neural network ansatz fixes for you the dimension of that field,
That's right.
right? So now let's say I want to compute the 4-point correlator of this field, uh,
Yes.
just this field, the 4-point correlator of identical scalars,
Yes.
and I go through this process on a neural network, which means in my head that means I initialize 1,000 times, and I just collect the values that I get. Um, uh, and then I compute the mean over those values, and that will give me the 4-point functions,
Yeah, that's right.
etc. So now that I have this 4-point function, how do I actually? So these are just numbers I have on a neural network. It's all just numbers.
Yeah, that's right. It's all just numbers.
So how do I extract the spectrum
Oh, oh,
from there?
okay, okay. So you're giving it a bunch of points, right? Uh, so
Yeah.
yeah, you're giving it a bunch of points. So what you do is you will plot the output with the i- input values that you're giving, uh, and then
So I just wanted to know. So let's say you get some output from the neural network. Are you going to compare that to the conformal block decomposition and then extract numbers to a fit
yeah,
with the conformal block decomposition?
yeah, I mean, first you have to like if you're doing it with just with numbers, then first you have to look at those numbers and learn the functional form, and then you can do the conformal block, like then you do the
Okay.
conformal block decomposition.
Okay. So I didn't understand in this whole business, where are interactions encoded? Like
Oh,
what tells me that this is a, so let's say there's a particular kind of interaction I want to encode. How do I encode that?
a very good question. So I am calling it an interacting field theory is because the connected 4-point functions they don't vanish if you subtract from them the 4-point
Yeah.
functions, the product of 2-point functions, then you get a non-zero answer. And
Mm-hmm.
you can so there's something called edgeworth expansion. So these theories are also not just non-local, they're all non-unitary. They're also, the example I showed you, it's also non-local. So uh, from the edge,
Which example?
the theta dot x example.
Why is it? Yeah, I mean, it's non-local in the sense that correlation functions are growing with distance.
Yeah,
But it's yeah, okay. But your fields are all local. They still only depend on one
fields are
and y.
local, fields are local. uh,
Okay.
um,
Yeah. Okay.
so uh, so what you can do is that you can do an edgeworth expansion and compute the leading order correction, or you can compute the first correction to the correction to the action. And there you can kind of get an idea about what kind of interactions are there, if you would like to write an action, uh, what kind of action it would look like. So to answer your question, I don't know how to do the theory for using neural networks. If I'm
I
interested
see.
in theory XYZ, I don't know how to encode that dynamics in the network.
Okay.
But what I know is that there is a way to construct theories from neural networks that have a conformal symmetry in their correlation functions. And my hope is that starting from these theories, I can start doing the theory. I can flow to the theory that I am interested in, and then ask questions in the theory that I'm interested in. So that's the hope.
Okay. Okay. Understood.
And
Mm.
if you think about training process, like if you're training it, then you can think of it as some kind of inverse RG flow. Uh, so so
So, how do you
yes.
make sure that as I'm training it, I am still I still have a CFT at or a
Oh,
CT at each point?
yeah, in general, you don't, because as you train it, your probability distribution might break the symmetries that are required for a CFT. So, in general, you don't. In general, you will go to some statistical field theory. Uh,
Okay.
but if you can take care of your training in a manner where the symmetry is preserved, or in a manner where you at least end up in some points where there is a CFT, then that kind of means that you're flowing from one CFT to another CFT.
Okay. Okay.
Uh,
I mean, so in the sense, if there's no training involved, there's no gradient descent. Uh,
no, there,
all of this can just be simply like I could do this in mathematics as well, right? I could just
yeah, that's right. You can do this in
because
mathematics.
I just need an ansatz, and you call the ansatz neural network. I can just call it an ansatz and
Yeah,
just
yeah. So I am constructing functions, and those functions are some ansatz for fields. And in my case, it happens to be that I chose those functions such that what people use in neural network literature.
yeah.
Yeah.
Yeah, I understand. Um,
But if you want to think of it from,
because the ansatz you're choosing for the field, that is just the so that is just the definition of the primary operator. So like if you demand that it's an it's an eigenstate of the dilatation, uh,
yes,
and you just demand that it has the proper, you'll just get that ansatz. Like it's analytically you'll just so it's not like the ansatz is a very it's just the solution of the it's just the definition of the primary operator. That's how it should look like.
yeah, the ansatz is just the definition of the field. And a field should also be probabilistic. So you are encoding certain type of probabilistic nature by um, putting it
Okay.
together with the weights, and uh, your correlation
Mhm.
function are then just statistics of those probabilistic expectation
Yeah.
values.
And the architecture, answers you choose for the field, that has nothing to do with the uh, interactions, right?
No, it has, because because if you change the function, then what would happen is that you can get complicated, some very strange, or like a different GUV you will get, and so your interaction has changed.
Uh, okay, okay. No, I just meant interactions would involve a field interacting with another field. Like
Yeah. So
that is pro-
yeah.
that is
So you can,
probably something that is encoded in the distribution.
um, I would say that
Yeah.
it is encoded in the full architecture,
Okay.
where it depends both on the distribution and also how I define the ansatz of the field. Let me just, maybe I should quit it too early. Um,
No, okay. I understand. I understand.
yeah. So this is a very simple thing. I could nest it with other things, and such that the end product is this. Then or even if I change this minus to plus, or let's say I take certain value, and I and also this distribution, probability distribution function, I take something very non-standard that respects the symmetries. Then 2 point
Okay.
and 3 point functions would be fixed as usual, but from the 4 point functions you would get extremely different dynamics, extremely different interaction.
I see. Okay. Okay. Thank you.
Yeah.
So, anyone, if there are no more questions, let's thank Joydeep again. So, okay.
Thanks, guys.
Okay. Okay.
Bye.
Yeah. Bye bye. Thank you for the talk. It was really nice talk.